Oh, well, welcome to this podcast entitled Altering Product Strength, Use of Stock Solutions, and Problem Solving by Allegation, which is a long title for basically saying this. We're going to be solving a bunch of questions that all relate about manipulating concentration. I love this chapter, although a lot of students hate this chapter, and it's because the light bulb hasn't gone on for them. But once it does, these are fun questions to try to figure out. But for now, you're probably going to find them very annoying because it truly makes you have to have a good understanding of what concentration means, because all of these questions will be altering the concentration in different ways to be able to come up with a new product. So with a little bit of background really about concentration is that the strength of a pharmaceutical preparation may actually be increased or decreased by changing the proportion of the active ingredient to the whole. A preparation can be strengthened or made more concentrated by either the addition of active ingredient or even by combining it with a like preparation of a higher strength. On the other hand, the strength of a preparation can actually be decreased or diluted with the addition of either an inert diluent or, again, mixing it with another product of a lower strength. A key point here is this, that if the amount of active ingredient remains constant, a change in the total quantity, whether it's volume or weight, of the preparation will alter the strength inversely. What this means is this, that the concentration decreases as the total quantity increases. And conversely, the concentration increases as the total quantity decreases. Now, in this podcast, we'll work through various examples of either starting with a product which we then alter by adding more active drug to it to make it more concentrated, or adding more diluent to it to make it less concentrated. We will also be solving most of these problems in two different ways. The first method is called the equation method, which uses the mathematical relationship of the concentration 1 times quantity 1 is equal to concentration 2 times quantity 2. So we'll be applying that, and it's much more of an algebraic method. Now, alternatively to using that way, we can also apply what's called the Alligation alternative method. And a lot of students actually prefer this method because it is much more visual. The way you set it up helps you actually see the high concentrations above and the low concentrations below, and it has arrows, and you can kind of follow along what's happening a little bit, and it's less algebraic. So what's important is that you can learn how to do both of them so that you can, on a test or in your own application, do one or the other. You don't normally have to answer the same question more than one way, but we want you to learn which way works best for you. So with that, let's proceed with our first question. All right, let's read our first question. It says, how many milliliters of an 85% weight per weight solution of lactic acid with a specific gravity of 1.21 should be used in preparing this following prescription? And the prescription calls for this: lactic acid 10% weight per volume, salicylic acid 10% weight per volume, in a flexible colloidin, which is kind of a gel base, with a total volume of 15 milliliters. And again, this product would be used for wart removal. So a little bit of background is that, and I can show you here, I just wanted you to have to see this really kind of gross picture of a wart because that's what we are compounding. We are essentially duplicating the formulation of the commercial product Duofilm, which you can see here contains both salicylic acid and lactic acid. So a little bit of background is that Duofilm is used on the skin to treat a common skin or foot, which is called plantar warts, and also used to help remove corns and calluses. Now, salicylic and lactic acid are both what they call keratolytic, meaning they help cause the wart to gradually peel off. They work by increasing the amount of moisture in the skin and dissolving the substance that causes the skin cells to stick together. This actually makes it easier to shed the skin cells. Now, keep in mind that warts are caused by a virus, but neither salicylic acid nor lactic acid affect the virus, which is why warts often or sometimes reappear after an incomplete treatment. You can get rid of all the top layer of skin, but if there's still a little bit of virus left in there, it can eventually grow back. So, having said that, let's perform these calculations in this preparation of this commercial product Duofilm. Now, so let's rewrite some important information and get rid of what we don't need to know and focus on what we do need to know. And we'll start with, what do we need to know from the prescription? Our question is really only asking about lactic acid, so we'll focus on lactic acid. And what it calls for lactic acid is a 10% weight per volume. Okay, as I said, this whole podcast is all about concentrations and understanding concentration. So understand what the prescription calls for is a 10% weight per volume. All right, and a total volume to prepare of 15 milliliters. Okay, that's what we're trying to make. What are we going to use to make that product? What we have is a lactic acid stock solution, and I'm going to abbreviate that LASS to separate it from LA, which we'll just refer to as the pure lactic acid. So to provide the pure lactic acid LA, we're going to use lactic acid stock solution, LASS. And what we know about this stock solution is that it has a concentration, though, that's expressed as, be careful here, 85% weight per weight. Okay? We also were given a specific gravity for that solution of 1.21. And really what this question is asking is, how much of that do we need? What is the volume of this stock solution we need to provide so that we can compound this prescription? So with that in mind, let's go ahead and start on the calculation. So I've rewritten some of that important information here. The first step is to determine the required amount of just lactic acid. The ingredient we need, lactic acid, how much do we need of that to compound the prescription? So I'll show you my formula here and we'll step through it. Where do we start? It's always hard to know where to start. We start with the amount of the final product we're trying to compound. So what we want is 15 milliliters of this wart remover gel. So let's start with a final volume of 15 milliliters. Okay. We are then going to multiply that by its concentration. The prescription asks us to compound a lactic acid at a concentration of 10% weight per volume. So we set that up here as 10 grams, because it's weight, over 100 milliliters, because it's a percent. And again, the lower part of the percent is in volume, weight per volume. We set it up this way so that you can see that when we now multiply, our units of milliliters will cancel, such that if we take 15 times 10 divided by 100, our answer will be 1.5. And you can see milliliters cancel, so our final answer of 1.5 is in grams of pure lactic acid. That's the amount of product or active ingredient we need. Step 2 has got 3 parts to it. We're going to take that weight and convert it we're going to convert it from the weight of lactic acid to the weight of the stock solution, and then finally from the weight of that stock solution to the volume of that stock solution. So with that, here's my formula for that. Let's go again, do this one step at a time. So where do we start? We start with the same answer we just calculated. We know that for the compound this prescription, we need 1.5 grams of lactic acid. Okay. Now, this is where it may get a little confusing for some of you, because we need to multiply it essentially by the concentration. Okay, so let's look up. What did it say about the concentration of the stock solution? It was given to us as 85% weight per weight. That means a quick rewriting of that would be 85 grams of lactic acid over 100 grams of the stock solution. Remember, it's weight per weight. So 85 grams of lactic acid for every 100 grams of stock solution. So now looking at this formula, though, we're going to multiply it by that concentration, where we will change it, though, and express it as there's 100 grams of the stock solution over the 85 grams of the lactic acid. And we do that so that our units can cancel. Grams of lactic acid will cancel, and now we will be in grams of our stock solution. And we're really close to our final answer, but we don't want to measure our stock solution by weight. We want to measure it by volume. So we want to convert from the weight of the stock solution to the volume of the stock solution. So to do that, we are going to use the specific gravity. Okay? We were given that the specific gravity is 1.21. Okay? And remember, that means grams of your product per gram of water. Well, since, again, the density of water is 1 gram per milliliter, we can really treat the specific gravity here as we do density. So essentially, we can have a 1.21 specific gravity is the same as 1.21 grams of stock solution for every milliliter. So now, looking the way we set this up, we set up the proportion of saying for every 1 milliliter of this stock solution, it would contain 1.21 grams of the stock solution. And we set that up so that the grams of stock solution cancel, and our final answer will be in milliliters. So if you do that math all the way from left to right, starting from 1.5 and work your way across, you should get a final answer of 1.46, and the units that remain would be milliliters of the stock solution, which is the final answer for this question. We've determined that we need 1.46 milliliters of stock solution to provide us 1.5 grams of lactic acid to be used in compounding this prescription. All right, our next question furthers this idea of manipulating concentration, but makes it more difficult in the sense that we will express that concentration as a ratio strength, which is often confusing for students, and also by specifying the amounts to use in the units of parts. And again, people don't like the used parts. That seems to be a problem. So let's practice. It's not that bad. So to read the question, it says, a 1 to 750 weight per volume solution of benzalkonium chloride. So keep in mind, that's what we already have. We have a stock solution of benzalkonium chloride already, and it has a concentration of 1 to 750 weight per volume. What we're going to do with that pre-existing solution is dilute it further with water. And we're going to do so in a ratio of 3 parts of this pre-existing benzalkonium chloride solution, 3 parts of that diluted further with an additional 77 parts of purified water. And we're doing it because this more dilute solution is what's recommended to be used as an bladder and urethral irrigation solution. And so the question, we're being told just to do that. So the question is, well, what is the ratio strength of benzalkonium chloride in the final dilution? All right. A little bit of background before we do the math about benzalkonium chloride is because of its antimicrobial activity, benzalkonium chloride is actually an active ingredient in many, many types of consumer products. So, for example, it's used as a preservative in pharmaceutical products used for the eye, ear, and nose. It's in personal care products such as hand sanitizers, wet wipes, shampoos, and deodorants. It's even used in skin antiseptics such as Bactine spray. It's often used in throat lozenges and mouthwashes, even in spermicidal creams, and over-the-counter applications for cold sores and fever blisters. And part of the reason it's so widely used is that the advantage of benzalkonium chloride, not shared by other alcohol or hydrogen peroxide antiseptics, is that it does not cause a burning sensation when you apply it to broken skin. So, antiseptic used for helping avoid bacterial infections in lots of different products. So, let's rewrite the information we need for this question. And it starts with this. The concentration of the solution we already have is a 1 to 750 weight per volume. Okay? And what we want to make, while we don't know what the concentration will be, we know the quantity. We know what we want in the end is 3 parts of the initial benzalkonium chloride solution mixed with 77 parts of water. So we do have a volume or a final quantity of the solution we're trying to make. So with that in mind, let's go ahead and answer this question. So I've rewritten some of that information, and I'll remind you what we are trying to solve for is the ratio strength of benzalkonium chloride in the final dilution. And the way we're going to solve this, and I'll go ahead and show you the whole answer. This is all of the equations answered and solved right here. The way we're going to answer it, though, is using what we call the equation method. And it's simply comparing or using the concentration initial times the quantity initial plus whatever you add to it times its quantity and concentration is equal to some final concentration and quantity. So we'll go through this step by step, but this is what we mean by when we say the equation method. So where do we start? Let's look at the first line here, and let's start on the far left. What we have are 2 things in parentheses. The one on the left is a concentration, and the one on the right is a quantity. So what we have to begin with is those expressed for our initial benzalkonium chloride solution that we already had made up. What was the concentration we were given for that? It was 1 to 750. So the first parentheses is the concentration expressed as 1 over 750. Concentration of our initial benzalkonium chloride. We're going to multiply times that, times the quantity. And I'm going to convert here from quantity to volume. Since we are talking about liquids in this question, therefore the quantity will be the volume. What volume will we be using of our initial benzalkonium chloride solution? We will be using 3 parts. And I know students don't like this because you want it in milliliters, you want it more specific, but we don't know that. We don't know how many milliliters we're going to use, but we know relative to the amount of water we're going to be adding, we're going to have a volume of 3 parts of this initial benzalkonium chloride solution. So the concentration is 1 over 750 times its volume, which is 3 parts. That describes our benzalkonium chloride component. What are we adding to that? How are we changing that? What we are adding to it is water. So let's use the same sort of concentration times quantity for the water we are adding. Well, what is the concentration of benzalkonium chloride in water? It's 0. There is none. So no benzalkonium chloride in water to begin with means it has a 0 concentration. So our first parentheses is 0 for 0%, if you will. Okay. What is the quantity? What is the volume? We have 77 parts. We were told to use 77 parts of water. So it has a concentration of 0 and a quantity or volume of 77 parts. And that's it. Those are the only 2 things we are adding together. We are adding our initial benzalkonium chloride solution to water, and we have defined both of those. So what we set that equal to is the combination of both. What happens when we add just those 2 things together? What is the final concentration? That's what we don't know. We're solving for that. So you'll see my first parentheses is X. I'm setting X equal to the concentration in a ratio strength format of benzalkonium chloride in this final combined mixture. And we don't know what that is. So that's X. And a lot of students do okay with that. This is where some people's minds get blown, and you just need to understand this. This is a key to all of these questions we're doing in this entire chapter, is that when you add a certain volume or a weight, but in this case we'll say volume, of one product to a volume of another product, the combined volumes are just simply additive. The volumes don't come from anywhere else. It's what you started with of one item plus what you added with the second item. What you have in the end are the combination of those 2 things. So we can actually say that we know what the volume of our final product will be. It will be the 3 parts from the benzalkonium chloride plus the 77 parts of water. There is no mystery. Those are the 2 things that make up the quantity of our final solution. And while we don't know its concentration, which is why we called it X, we do know and can predict its final quantity as being 3 plus 77, essentially 80 parts total. That's all we need to do. That answers this question. All we have to do now is solve the algebra, which is why this equation method certainly requires a certain skill in algebra, and I'm not going to be reteaching all of that algebra. Hopefully you can follow my work as we go along, but we now just solve for X algebraically. So what I do is let's go ahead and combine all of the 2's concentrations and volumes together. So you can see if we start with our benzalkonium chloride and take 1 over 750 times 3 parts, we get 3 over 750. And let me say, when we do this method, when we do the algebraic method, it's very important to go ahead and set up the very first line with all of the units so that you can make sure that each numbers are being expressed in the same units. So we're parts all the way across, and we will have our final strength and ratio all the way across. Okay, but after you set that up with the initial line, do not carry the units as you solve for X. It will mess you up. Students make mistakes. So at this point, you'll notice I don't include any units till the very end. So with that, going back, 3 parts times 1 over 750 is 3 over 750. To that, what are we adding? We're adding 0 because 0 times 77 is 0. And then what did we say that equals? Now we got to multiply x times 3 plus 77. That's 80. So 80 times x is 80x. So we essentially know that 3 over 750 equals 80x. Now to solve for x, we're going to divide both sides by 80 to get rid of the 80 with the x. So now what I have on the left-hand side, well, on the right-hand side, I just have x since I divided both sides by 80. What I have on the left-hand side is just combining the fractions is 3 over the 750 now times 80 since we divided by another 80. All right, so if we just kind of combine that by multiplying 750 times 80, you can see that's the same as expressing it as 3 divided by 60,000. And lastly, let's divide both the numerator and the denominator of that fraction by 3. So we get a final answer of 3 divided by 3 is 1, which is why we have 1 on top. And 60,000 divided by 3 is 20,000. And that's our final answer. What we now have is that x is equal to 1 over 20,000. And hopefully you're able to follow the math to get to that number. And go back to our the first line of that equation. What did x represent? X represents the concentration of benzalkonium chloride in our final solution, expressed as a ratio strength. So when we mix all of those things together, what we get is a concentration of 1 to 20,000 weight per volume of benzalkonium chloride. And that is essentially the answer to this question. All right, this question is somewhat similar, but in this case, we're going to be trying to solve for the amount of water to add. So it's a variation from the type of question we just answered. So let's start with the question. It reads, how many milliliters of a 1 to 50 weight per volume boric acid solution can be prepared from a 500 milliliter volume of a 5% weight per volume boric acid solution? So before we jump into the math, a little background is that boric acid, like benzalkonium chloride, is actually used in many different types of products. Now in medicine, boric acid is often used as an antiseptic for the treatment of minor burns or cuts and is often included in ointments or even in wound dressings for that purpose. Now, a dilute boric acid solution can be used as a vaginal douche to treat bacterial or yeast infections. However, that same kind of solution could be actually diluted much more to a very dilute solution and actually used as an eye wash. So getting back to this question, essentially what we're doing is that we already have a 5% solution, and we'll say that solution is more appropriate to be used as a vaginal douche, but what we want is to use that solution to create a much more dilute solution that would have a more appropriate concentration to be used as an eye wash. So let's rewrite the question information and really distinguish what we're starting with initially from what we want to end up with. So what we're starting with initially is a solution that has a concentration of 5% weight per volume. We also know that that solution we're starting with has a total volume of 500 milliliters. Okay? What do we want to end up with? We want to use that solution and add some water to it to make a final solution, and that final solution wants to have a concentration of 1 to 50 weight per volume. And what we're solving for and what we don't know is when we make that, what will our final volume be? So with that, let's go ahead and start to answer this question. So here's some of that same information rewritten. We're actually going to start this question with something of a pre-step, because what I don't like, what I can't really use, is expressing our final concentration as a 1 to 50 weight per volume. What I want to do first is let's just convert that to a percent weight per volume. So we'll set it up this way, and I'll kind of work you through here. What we're starting with, though, in the question was that we have a 1 over 50, a 1 to 50, and since it's a weight per volume, we have units of weight over volume, okay? What I want in the end is to express that in a percent weight per volume. And percent weight per volume is defined as, percent weight is the weight in grams per 100 milliliters. So if my ratio strength is 1 over 50, I'm going to set that equal to some X grams for weight over 100 milliliters because that's defined as percent weight per volume. So now all I need to do is cross multiply. So I would get 50x cross multiplying equal to 100. If I divide both sides by 50, I see that X equals 2, and it would essentially be 2 grams per the 100 milliliters, which is the same as 2% weight per volume. So a 1 to 50 ratio strength is the same as a 2% concentration. All right, so that's the number we're going to use for our final concentration from here on out in this question. All right, now we're actually going to solve this question two ways. The first way we're going to solve it is using the equation method, which was similar to our previous question for benzalkonium chloride. Okay, we're going to set up the equation method to realize the first thing we're actually going to solve for is the volume of water, and then we'll actually figure out the final total volume. All right, so here is the equations all set up and completely solved for you, and we're going to go through this one step at a time again. So starting on the far left, we said, I'll remind you, the equation method uses the concentration times the quantity of the first ingredient plus the concentration times the quantity of the second ingredient equal to some final concentration and quantity. All right. So our first combination on the far left in parentheses is the first concentration. And what we're going to start with is our initial solution. And we know that the concentration of our initial solution was 5%. We were given that. Okay. We're going to then multiply that by the quantity we have. And I will, again, in this question, all of our quantities will be expressed as volumes, not weight. So I'm going to just refer to my quantities as volumes. Okay. So what we were told is that this 5% solution that we have, we're starting with 500 milliliters. We were given that volume initially. So our first quantity times concentration is 5% times 500 milliliters. That's our initial starting concentration of the boric acid solution. Okay, what are we adding to that? We are adding to that water. Okay, so what is the concentration of boric acid in water? 0. There is none. There is no boric acid in water, so its concentration is a 0%. What volume of water are we going to add? We don't know that. That is what we are solving for in this equation. So let's set it equal to X. X equals the number of milliliters of water to add. Okay, so we have 0% for the concentration times the volume of water we're going to add, which we have set as equal to X milliliters. All right. Now, those are the only two things we're adding together. So when we add those two things together, combine them, what are we going to end up in the end? Well, we know what the final concentration is desired to be. We want the combination of the amount of water plus our stock solution to equal 2% concentration. That's what we just solved for in our pre-step. So we have it equal to our concentration of 2% in parentheses times some volume, some quantity. And this is kind of the mind-rending step for a lot of pharmacy students here. We know the volume. We can predict the volume because remember, volumes are additive. They just don't appear from nowhere. So what did we start with volume-wise? We started with 500 mils, right? That's the amount of our stock solution. And we're adding to it some volume of water, right? We don't know, but we assigned it. What did we assign that volume? We said that volume is equal to X. So our final volume will simply be the 500 plus the X, and that's what we set this equal to on this formula. So on this side, our concentration is 2% times the volume, which is 500 plus X. That defines the final volume we'll have. And that, I will still say, once you can conceptually understand that, then these equation method formulas become much easier to solve. So hopefully you understand it at this point. All right. Now, I said the first line in this first step is very important to plug in and use all of your units so we can see that all of our concentrations are expressed in percent. And we can see that all of our volumes are expressed in milliliters. But as we now solve this algebra to solve for X, do not carry those units forward. So let's just simply start combining some of these numbers. So on the far left, if I take 5 times 500, and again, ignore the units here, just use the numbers that we have. 5 times 500 is 2,500. That's our first number. Plus 0 times X is 0. And we set that equal to, now we need to kind of carry our 2 times 500. So 2 times 500 is 1,000. Plus 2 times X is 2X. So that's our first step in solving for X. Now let's subtract 1,000 from both sides. So if I subtract 1,000 from 2,500, I would get 1,500 on the left, and that would equal on the right then just 2X because we subtracted 1,000 from both sides. Now all I need to do is divide both sides by 2. So 1500 divided by 2 is 750, and that would just equal x. So we have solved for x. But I'll remind you, now we go back to that first line. What did x represent? X represents the volume of water to add in milliliters. So we now know to add 750 milliliters of water to our 500 milliliters of our 5% solution to get a 2% solution, but we haven't quite figured out our final total volume. So our last step, which is an easy one, because the question wanted us to actually determine the total volume that could be prepared. So let's just summarize what we already know. We now know we are starting with 500 milliliters of the 5% solution, and we've just determined that we're going to add to that 750 milliliters of water. So you add 500 to 750, you can see where your final answer would be 1,250 milliliters. And I'll just remind you that final volume, which is our answer, would have a concentration of 2%. And that is the answer to this question. But we are not done. Oh no, we are not done. Because now I want you to be able to solve this same question using a different method called the allegation alternative method. Okay? You don't have to solve it this way. You can solve it using the equation method, especially if you're good at algebra. However, it's important that you learn how to solve these questions using this alternative method. And I'll say a lot of people really prefer the allegation method. It's a little hard to understand at first, but once the light bulb comes on, it's a much more visual way of approaching these more difficult questions, and it doesn't involve near the amount of algebra. So a lot of students do prefer it this way, but it takes a little bit to figure out. So let's see if I can help you figure out how to solve this same question using the allegation alternative method. And I've set up all my entire formula here, so don't get overwhelmed at first. Well, let's go through this one step at a time. And it starts on the very top left. We are going to set up kind of a triangle. I visualize it as a triangle. And the very top left of the triangle is the high strength solution that we are using. So what is the high strength in this question? 5%. So we're starting with a 5% solution. So 5% goes on the very top left. Then what goes directly below that number, okay, is the low strength. What is the low concentration that we're mixing with our high strength? Well, we're mixing it with water, and we know water has 0% drug in it. So bottom left is 0%. So top left, 5, the high strength. Bottom left is the low strength, in this case 0%. Then what you do is in the middle, to the right, you put the number of your desired concentration. What do you want to make from those two ingredients? What we want to make is a 2% solution. So can you see, kind of visualize a triangle with the top left being the 5%, the bottom left being the 0%, and in the middle to the right is the desired concentration of 2%. Once you set that up, then what we're going to do is follow the arrows. You go diagonally and you cross subtract. And you always subtract the higher number from the smaller number. So it's always a positive number. Always take the large number and cross subtract the smaller number. So in this case, we'll take our 5 minus the 2 to get a value of 3. And notice when we cross subtract and go down diagonally and write our value of 3 down below there, following the arrows, we no longer carry over the units of percent. Do not carry the units over. It's just a number. So 5% minus 2% gives us the number of 3. Okay? I'll come back to the units here in a minute, but it's not percent anymore. So just leave it be and write the number 3 down there. Okay? Now let's do the same thing going in the opposite direction. So going diagonally from the lower left up to the upper right, we're going to take the 2% minus the 0% and get the number 2. So you can see that we've cross-subtracted and gotten our values of 2 and our value of 3. Now notice the lines going horizontally from left to right. So on top there where you see the 5%, you can see an arrow kind of going horizontally over to the 2, because the 2 value and what we solve up here on top with the 2 value is the amount of the 5% we're going to need to use. Similarly, down below there, under the 0%, can you see the arrow going horizontally from the 0% over to the 3? So the numbers we get solving using the 3 value there will represent the amount of water. Okay? Now, this is very important. Hopefully you understand where we got the 2 and we got the 3. We cross-subtracted. The next step is actually to simply add those two numbers together. So what is 2 plus 3? That is equal to 5. And now I'll bring up, when I say we don't, in terms of units, our numbers here, our 2s and our 3s and now our 5s represent parts. Okay, the 2 and the 3 represent the individual parts. The 2 represents the number of parts of the 5%, whereas the 3 on the bottom represents the number of parts of the water, or the 0%. But we now know the total number of parts, which is 5, because our next step is to simply divide our 2 and our 3, or write a line underneath those, and put the total number below it. So to summarize, up on top, if we go from the 5%, follow the arrow horizontally, we're saying for the 5% solution, what we need is 2 parts of that out of 5 total parts. Okay. On the bottom, if we follow the 0% line horizontally, when we cross-subtracted, we got the number 3. So we now know we need 3 parts of water out of a total of 5 parts. Okay. So that's all we've done is set up a proportion now. Okay. Let's start up with the 5%. Because the only other information we were provided in this question was that we are going to be starting with 500 milliliters of that 5% solution. So what we can do is set up our proportion now in this way, because we know for the 5%, we want 2 parts of the 5% solution out of a total of 5 parts. So let's set that equal to the amount of the 5% that we had to start with, which we were told was 500 milliliters, and set that over X. And understand what X represents now is the total volume. We know that we want a ratio of 2 parts of our 5% to 5 parts of the total solution. So we can set that equal to the amount of the 2% or the 5% we're starting with, which is 500 mils, over X. And now when we solve for X, by simply taking 5 times 500, which is 2,500, divided by the 2, if we just solve for X, we see that X equals 1,250 milliliters. And that is the volume that represents the total volume of both our 5% and our water mixed together. We know those two need to equal 1,250. And you should remember that as our final answer from when we use the equation method. That's the same answer. We just answered the question that we just solved previously using the equation method. We got 1,250 mil total volume. And that's the end of that question. But I do want to go one step further, because what we haven't yet directly solved for using the alligation method is the amount of actual water. We now know above there how much total solution we're going to have, but watch. We can do this same sort of proportion down below. But using the proportion below, what we know is we need 3 parts of water for every 5 parts of the total solution. We could set that equal to some X, which is now the amount of water. We haven't solved directly for the amount of water to add, but we know the total solution will be 1,250 milliliters. We just solved for that. So now if we do the math and basically take 3 times 1,250, so we get the 3,750 divided by 5, you can see we solve for X, and X would equal 750 milliliters. And that X in this formula represents the volume of water. Okay? So to summarize, and it's the same summary we did before, we were told to start with 500 mils of a 5% solution. But using the alligation method, you could see we solved directly that we can determine that we need 750 milliliters of water. And that would give us a total volume of 1,250 milliliters of what in the end would have a final concentration of 2%. Okay, so hopefully this was helpful in helping you see that you can solve these types of problems using either the equation method or the alligation alternative. And they will, in the end, produce the same answer. All right. This next question is going to be, one of the big changes is we're no longer going to be talking about our quantities and volumes, but solving these same questions and in the same way, but it also works just fine when our quantities are in weight, okay, in grams versus milliliters. So let's read the question. It asks, how many grams of salicylic acid should be added to 75 grams of a polyethylene glycol ointment in order to prepare an ointment that contains a final concentration of 6% weight per weight of salicylic acid? And let's just quickly point out on these slides that SA will stand for salicylic acid, And the PEG or PEG will be an abbreviation for the polyethylene glycol ointment base. Okay. Let's a little bit of background. Would you ever really make such a thing? Well, hopefully you can see on the commercial product here. Absolutely. Salicylic acid is very commonly used topically to treat a variety of skin conditions such as psoriasis, acne, warts, corns, and other dry and scaly skin conditions. Now, it works by actually increasing the amount of moisture in the skin and actually kind of removing some of the basement membranes so that it actually helps shed the dead skin cells from the outer layer of the skin. So, with that as a background, let's focus back on the question here. Let's rewrite three things. And this is in this question, you've got to divide this into three parts. What we know. First of all, what are we starting with? What are we adding? We are adding salicylic acid powder, and we have bulk powder to use, which means 1 gram of salicylic acid powder has 1 gram of salicylic acid. It's pure. Concentration is 100%. This bulk powder is pure 100% salicylic acid. That's what we're adding. But we don't know how much to add, so realize we're solving for that. Our question is, how much of that salicylic acid powder should we use? Okay, that's our first ingredient. Our second ingredient is what we're going to be mixing the salicylic acid into, which is this ointment base, this polyethylene glycol or PEG ointment base. We know quite a bit about the PEG ointment base. We know that its concentration of salicylic acid to begin with is 0. It doesn't have any. So its concentration to begin with is 0% weight per weight of salicylic acid. There's none in there. We also know how much we're using. We know to start by using 75 grams of this ointment, right? And those are the only two things we're adding together. The third thing we know, though, is what we want it to be in the end. So what do we want our final ointment to contain is a concentration of 6% weight per weight salicylic acid. Okay, so we know a desired concentration in the end, but we don't know what the final weight will be, but we do know what we want its concentration to be, which is 6%. So with all of that, that's all the information we need to solve this question. So I've rewritten this information here, and the first way we're going to solve this method is using the equation method like we've done before. So let's set it up here, and I'll step it through step by step. Starting on the far left, we have a concentration times the quantity of our salicylic acid. And we said that the concentration of our salicylic acid, since it's pure powder, is 100%. That's its concentration. Its quantity, and this is where now I will refer to quantity by the term of weight or grams. We're not doing volume in this question. Our percents are all weight per weight. So our quantity is weight. And what we don't know in this question is the amount of salicylic acid to add. So let's set that quantity, that weight, equal to X. X equals the weight of salicylic acid to add. So that's why we're going to multiply our 100% times X grams. Okay, so that's our powder. What are we going to add our powder to? We're adding it to that PEG ointment base. And what we know about the PEG ointment base is it has no salicylic acid to begin with, so its concentration is 0% times, we do know the weight of that we're starting with. We were told to start with 75 grams of this PEG ointment base. So our concentration is 0% times its quantity or weight, which is 75 grams. And those are our only two ingredients. We're adding a certain amount of powder to this ointment base. So when we combine those two things, what do we have in the end? What we want to have in the end is an ointment whose concentration is 6% salicylic acid weight per weight. So that's why we set the concentration equal to 6%. That's our desired concentration. What will our final weight be? And this is, again, the mind-blowing part. Understand the final weight of our product will be the sum of the individual weights. And we said we're going to add some X grams of salicylic acid powder to 75 grams of ointment. That's it. Those are the only two things that can contribute to our weight. So our final weight will be X plus 75 grams. Okay? So, and you can see in looking at this first line that all of our concentrations are expressed in percent and all of our quantities are expressed in weight of grams. So as we solve for X now, let's not carry our units along any further. So as I go on the far left, 100 times X is 100X. That we're adding to 0 times 75, which is why it's 0. And set that equal to, if we take 6 times x, we get 6x. And add to that 6 times 750, 6 times 75, which gives us a total value of 450. And that's how we ended up with the second line. So now to simplify this, let's subtract 6x from both sides. So if we subtract 6x from 100x, we can see that's why we get 94x. And set that equal to, if we subtract 6x, the 6x disappears, and we have just the 450. Now to solve for x, all we need to do is divide both sides by 94. So that's why we have 94x divided by 94 just gives us x on the left side. And 450 divided by 94 gives us a final value of 4.79. Okay, now let's quickly jump back up to the first line. What did x represent? It represented the weight in grams. So x equals 4.79 grams of salicylic acid to add. That's the weight to add to our ointment base, 75 grams of our ointment base. We mix all that together. We're going to get a final concentration that has 6% ointment. Okay, and that's the answer to this question. We know to add 4.79 grams of salicylic acid. But that would be too easy because we also want to make sure you could solve this same exact question using the alligation alternative method. So let's see if we can come up with our final answer, which we just said was 4.79 grams of salicylic acid, but doing it in an entirely different way. So here's the entire alligation set up. Let's step through this one step at a time. I'll go a little bit faster than I did the first time. Remember, let's set up our triangle. Top left is our high strength. And we said our high strength in this case is pure salicylic acid powder, which is 100%. Top left. What goes on the bottom left is the other ingredient we're using to mix with it, which we said was the polyethylene glycol ointment, which had 0% salicylic acid. So we put a 0% on the bottom left. What goes in the middle to the right is our desired concentration, which we desire is 6%. So our next step is to cross subtract. So starting on the top and going diagonally, following the arrows down to the lower right, 100 minus 100% minus 6% gives us 94. And remember, do not carry over the units. It's just the number 94. Do the same thing diagonally going from the lower left to the upper right. So take 6% minus 0% to get the number 6 with no units attached with it. So we have 6 on top that goes with the 100% if you follow the arrows horizontally. And down below we have the 94 that represents the value or the amount of the polyethylene glycol, 0%. All right. The next step, don't forget this part, is to combine those two numbers together. So what is 6 plus 94? That gives us a total of 100 parts. Remember, we really are now in the units of parts. So let's convert our 6 and 94 into the fraction we need. And the fraction we need on top for the salicylic acid powder is that we need 6 parts of salicylic acid powder for every 100 parts total combination. And on the bottom, we can see for the polyethylene glycol, we need 94 parts of that polyethylene glycol ointment per every 100 parts of the total combined mixture. All right. Now we have our proportions. Now what are we going to set up? What other information do we need? Let's start at the bottom. The only other information we have at this point is that we know we're going to be starting with 75 grams of our polyethylene glycol ointment base. So let's use the proportion of 94 parts of the PEG ointment over 100 parts total combined mixture and set that equal to our 75 grams of polyethylene glycol ointment that we're starting with over X. And remember, X represents the total combined weight. So if we solve for X here, 75 times 100 divided by 94, you would see that the total combined weight of our final ointment would be 79.8 grams. And that is the weight of our final, which we now know is set up to contain 6% of our salicylic acid. Now, intuitively here, you could simply say, well, if our total weight is 79.8 and we started with 75 grams, I could just subtract that. And if you subtract that, you would get your 4.79 grams. But let's continue to use this alligation method here to actually solve for the amount of salicylic acid. So let's go back up to this top proportion. This top proportion said that we needed 6 parts of pure salicylic acid for every 100 parts of our combination mixture. We can set that equal to still what we're solving for is the now unknown amount of salicylic acid powder, but we now know we can set it over the total combined weight. We know the combined weight mixture, since we just solved for it, is going to be 79.8 grams. So now, if we solve for x and take 6 times the 79.8, divide that by 100, x would equal 4.79, and that would be grams, and since it's on top of the pure salicylic acid. Okay, and that matches our answer from before. So just to summarize, and it's the same summary as before, but you can see using this alligation method, we just determined we need 4.79 grams of pure salicylic acid powder, and that's why it's 100%. To that, we're going to be adding what we were told to add, 75 grams of our pure polyethylene glycol ointment with no salicylic acid, and we can see that our final combined weight would be 79.8 grams, and that final ointment with that weight would have a concentration of 6% weight per weight of salicylic acid. So again, 2 alternative methods for answering this question. Well, I'm excited because we've made it to the last question, and I love this last question because it's about compounding. So before we even jump into the math or the actual question itself, you need a little bit of background to understand the context of this question. So we are a pharmacist who compounds a capsule. And what is a capsule? Make sure you understand. Capsule essentially is just dry powder encapsulated within a hard gelatin capsule. Okay, and you can see that on this picture here. A picture, when you open up a capsule, there is the body on the left and the cap on the right. Open it up and powder spills out because essentially a capsule is simply powder contained within a gelatin shell. But what you need to know is that when compounding capsules, it's important to know that the capsule shells should have enough total powder to be slightly packed. Having enough powder to almost completely fill a capsule is illustrated in this picture. However, keep in mind that many drugs which would serve as the active ingredient in a capsule are so potent they require very little weight. The weight of some active ingredients required in a single capsule dose might be 1 milligram or even less. That would not be near enough powder to sufficiently fill a capsule. Therefore, most capsules contain a powder mixture of both an active ingredient and an inert filler powder. Very commonly, that powder is lactose. So often I may even refer to lactose in this question. When I say lactose, I'm referring to the diluent powder that's mixed with the active ingredient such that there would be enough total powder mixture to fill a capsule. So keep in mind, the take-home message here is that the powder in a capsule is not pure drug. Rather, it is a mixture which has a concentration that would contain an active ingredient at some concentration. Thus, determining how to formulate a capsule at a desired powder concentration is the basis for this question. So now we can turn back to the actual question. The question reads, a drug is commercially available in a capsule, each containing, so per capsule, 12.5 milligrams of drug or active ingredient and 37.5 milligrams of diluent, or as I stated, something like lactose. How many milligrams of additional diluent or lactose must be added to the contents of one capsule to make a dilution of 0.5 milligrams of drug or active ingredient in each 100 milligrams of total powder mixture? Okay. So this question is made more difficult by the information they give us is different for both the previous capsule and the final capsule. So let me just summarize what we have, and then we're going to have to convert some things here in the middle. So what this question has told us for the current capsule is that it contains active ingredient of drug, pure drug, of 12.5 milligrams per capsule. It also told us that per capsule, the amount of diluent, in this case like lactose, that's in there is 37.5 milligrams, and that's again per capsule. Then, separating your mind, that's what we got to start with. What we want to make in the end is a new capsule. And essentially, the concentration of powder in this capsule has to have essentially 0.5 milligrams of active ingredient in a total powder weight, a combined weight of 100 milligrams. All right. So let's just move on, because this is kind of the numbers we have here don't help. So let's start by really re-expressing some of these informations. What we need to wrap our mind around this question is, let's do this. Let's actually look at the current capsule and express its current concentration, but in as a percent weight per weight. So what is the percent amount of active ingredient per weight of this capsule? Okay, so to do that, we have everything we need. Let's just re-express it. So let's do this one step at a time. What we know about the current capsule is that there is 12.5 milligrams of active ingredient or drug in the capsule. That's the amount of active ingredient, 12.5 milligrams. So let's set that on top. Let's divide that by the total weight of the capsule. But what we know for the total weight is that the total weight would contain 12.5 milligrams of active ingredient. We were told that. Plus the 37.5 milligrams of diluent. The other number they gave us was the amount of diluent, which was 37.5. So the total weight on the bottom would clearly need to be the combination of both active ingredient and diluent. And if you take the 12.5 plus the 37.5, you can see that total weight would be 50 milligrams. So essentially, we have 12.5 milligrams of active ingredient divided by a total weight of 50 milligrams. And if we multiply that by 100, we see that our actual percent weight per weight would be 25%. And that's what we already have. We're not changing anything. That's the capsule we are starting with. Has a starting concentration of 25% weight per weight of the active ingredient. So now let's figure out where we want to go. What do we want our final capsule to be? Again, expressed as a percent weight per weight. All right, let's do the same sort of thing, but with our final situation, because what the question told us is, in the end, what we want is to have 0.5 milligrams of active ingredient. And in this case, it did tell us the total weight. It said in a total weight of 100 milligrams. So all we have to do is take the 0.5 milligrams of active ingredient, divide it by the 100 milligrams total weight, times 100% to convert it into percent, and you can see the number would be 0.5% weight per weight of our active ingredient. So this is starting to sound more like some of the questions we've already answered, because what we have is a currently high concentration of powder in our capsule at 25% weight per weight, but what we want to do is reformulate it with enough diluent powder so that we lower the concentration down to a final concentration of 0.5%. Now that I see that information, I know where to go, because I've worked all of these questions and I know I'm going to start off with the equation method. Let's solve this question using the equation method, because what we have here, and I'll set it all up here and we'll work through it one step at a time, is we have a capsule that we're starting with. And we just solved and said that that capsule has a concentration of 25% weight per weight. We also know that the total weight of that capsule, by the time we added the diluent and the active ingredient together, we said that that total weight is 50 milligrams. Okay, so we have a concentration, 25%, and a quantity of 50 milligrams. So let me just clarify here, as far as quantity goes for all of this question, we are going to be in weight. Okay, but here now we will be using the units of milligrams. So our quantity should be expressed in weight, and that weight will define in milligrams. All right, so our first concentration and our first quantity. That capsule, what are we adding to it? We are adding to it our diluent, our lactose in this case, right? So what is the concentration of our active ingredient in the diluent to begin with? 0. There's none. There is no active ingredient in our diluent. It's pure diluent. So it's 0% active ingredient in there. How much of that diluent are we going to add? We don't know. That is what we are solving for. So we'll set that equal to X. X equals the weight of diluent to add in milligrams. All right. So we have a concentration of 0% times a quantity of X milligrams. All right. Well, those are the only two things we're adding together, so what will we have in the end? Well, what we want to have in the end is a powder that has a concentration of 0.5%. We just calculated that. That's our desired final concentration, right? What will we have as far as our total weight in the end? We know that because it's additive. There's only two things mixed together. We are mixing 50 milligrams of our initial capsule plus some X milligrams of additional diluent. We don't exactly know how much it is, but we have assigned the amount of additional diluent to X milligrams. So our final weight will be 50 milligrams plus X milligrams. That will be the total weight of powder we have, and we want that concentration to be at 0.5%. So now, let's double check our units all the way across that all of our concentrations are now expressed as a percent weight per weight, and that all of our quantities, our weights, are expressed in the units of milligrams. So now as we go forward, let's not carry the units forward. So starting over on the left again, 25 times 50 would give us the 1250. To that, we're going to add 0 times X would be 0, so that value is 0. And that would be equal to, let's take 0.5 times 50, that would equal the 25, plus the 0.5 times X, which would be 0.5X. Next, let's reduce this by subtracting 25 from both sides. So if we do that, then on the left-hand side, we would have 1225, and that would equal to just 0.5X. Lastly, let's divide both sides by 0.5. So our final answer would be, again, the 1225 divided by 0.5 would be 2450, 2,450. But let's go back up to our first line and remember, what did X represent? What our answer means is that we have 2,450 milligrams of diluent. That's the amount of lactose or diluent to add to our capsule to make our final correct concentration at the end. And that's the answer to this question. We want 2,450 milligrams of lactose to add to our capsule. But we're not done because it would be no fun just to solve it one way. So let's solve the same exact question and see if we can come up to the same answer of the 2,450 milligrams using the alligation alternative method. So setting this up and showing you, and let's go through it one step at a time. The very top left represents our high strength or our high concentration, which is our current capsule. Our current capsule has a 25% weight per weight concentration. So that goes on the top left. What goes on the bottom left is what we're mixing it with, which is a pure diluent, which has 0% drug in it. So we have a 0% on the bottom left. What do we write in the middle to the right is our desired concentration, and what we desire is 0.5%. So next, let's follow our diagonal lines and cross-subtract going from the top left to the lower right. So 25% minus 0.5% gives us the number of 24.5, remember, with no units. Now, let's cross or subtract going the opposite direction from the bottom left to the upper right. 0.5% minus 0% gives us the number of 0.5, again with no units. Those are our numbers. So the next step would be to add those two parts together. So if we have 0.5 plus the 24.5, we would have a total of 25 parts. So setting up the fraction on top for the pure capsule that we have, the capsule we're starting with, we can see that we need 0.5 parts of that powder for a total combination of 25 parts. All right. Now, what we already know about that is we know how much of that capsule powder we're starting with. We had a 50 milligram worth of capsule powder. So if we set that equal to 50 milligrams over X, what we are solving for is the total weight of powder that 50 milligrams of initial capsule powder needs to reside in. Because remember, our proportion was 0.5 of our capsule powder over a total diluted weight of 25 parts. Okay, we solve for X, so 25 times 50 divided by 0.5, and what we have solved for, we get a number of 2,500 milligrams. But remember, the bottom number there represented the total weight. That's the total weight that the 50 milligrams of capsule powder has to be diluted into. Okay, So our next step would be to take the 2,500 milligrams and use the equation down below for the diluent, because the diluent proportion said that we need 24.5 parts of diluent for every 25 parts of total mixture. We can set that equal to some unknown amount of pure diluent, but we now know the total mixture weight we're going to need to have is 2,500 milligrams. We just solved for that. So now when we solve for X, we are solving for just the weight of the diluent. And we do all of that math across, you can see that X would equal 2,450 milligrams, and that now represents the diluent weight. So just to summarize, the same numbers we just did with the equation method is that we are starting with 50 milligrams of a capsule powder that has a 25% concentration. That's our initial capsule. To that, we've just determined that we're going to add 2,450 milligrams of diluent with just pure lactose. When we mix those two things together, we'd have a total weight of 2,500 milligrams, and that amount of powder would have our final concentration that we wanted at 0.5%. So that ends this question as well. Hopefully you found this podcast useful and really being able to learn and apply two different methods of applying these sorts of questions where you must adjust the concentration. So there was the equation method and the allegation alternative method. Two different methods that can help you calculate the same numbers when you're looking at changing concentrations and either increasing them or decreasing them. And these concentrations could either be liquid, weight per volumes, or solids, weights per weight. The questions essentially are solved in the same manner.